Hi, I'm Fernando Pereira from Brazil, and today I will show you how to implement a live range splitting strategy. In other words, given a live range splitting strategy, I will show you how to build a program that presents the single information property for that strategy. Let's introduce the notion of a meet node first. These are nodes where different information collide. In the case of a forward analysis, meet nodes must be blocks with multiple predecessors. If we talk about a backward analysis, then a meet node must be a node with multiple successors. But there is no easy way to know what the meet nodes are exactly. As I said before, they are nodes where different data flow facts collide. However, we don't know where is different information colliding unless we solve the analysis. So we can approximate the set of meet nodes using the same techniques that we saw when we were talking about SSA form. In this case, we use the notions of dominance and iterated dominance frontier to find the set of meet nodes in a program if you're talking about a forward analysis. We can find the iterated dominance frontier of a node as the fixed point of these equations down here in the figure. Maybe before I talk about them, you can simply stop the video and try to figure out what the equations are doing. Let's try some exercise to understand the notion of dominance frontier. Can you grab a piece of paper and then try to find the iterated dominance frontier of every node that's marked in these figures? You can stop the video to think about the question. Here they are, the iterated dominance frontier of those nodes. Look at node I, for instance, here. We have K in the dominance frontier of I, and then we have L in the dominance frontier of K. And then we are done. These nodes make up the dominance frontier of node I. So, as a way to approximate meet nodes for a forward analysis, if information appears at some basic block, then we need to split live range of variables in the iterated dominance frontier of that block. For a forward analysis, we split live range creating 5 functions. Can you check where we would place 5 functions to split live range of a variable v defined at f in this example? Assume that we have a variable v being defined here, and that information is associated with this definition. Here they are, the 5 functions. We have inserted a 5 function at every node in the iterated dominance frontier of the block where v is defined. Notice that if we split live range like this, we might create 5 functions in the program with undefined arguments, like the 5 function on the top of the CFG here. To avoid this problem, let's assume that every variable is defined at the beginning of a program. We have a definition of v here. Similarly, we can have 5 functions defining variables that are never used. To avoid this problem, let's just assume that we have a use of every variable at the end of the program. Like here we have a use of v. Now, if the analysis is backward, we act in the same way as before, but we invert everything. So instead of talking about dominance, we talk about post-dominance. Similarly, instead of talking about dominance frontier and iterated dominance frontier, we shall be talking about post-dominance frontier and iterated post-dominance frontier. And we can compute the iterated post-dominance frontier of a node using these equations. If you want, you can stop the video and read them carefully. Before we move on, let me just clarify what's post-dominance. In node N, post-dominate another node M if every path from M to the end of the graph goes through N. So can you tell what are the relations of dominance and post-dominance in this figure? Just stop the video and try to see what are the dominators and post-dominators in these figures. In the first case, here, A dominates B and B post-dominates A. We say that they are control equivalent, because if A executes, then B will execute too. In the second graph, N post-dominates M, and in the third, X dominates Y. Notice that Y does not post-dominate X, because there exists a path from X to the end of the graph that does not go across Y. So can you tell me what's the iterated post-dominance frontier of these nodes marked in red? You can stop the video and solve this exercise. Here they are, the iterated post-dominance frontier of every node. Let's think about C, the last exercise. Here. C belongs to its own post-dominance frontier because it's a successor of itself and does not strictly post-dominate itself. By definition, a node cannot strictly post-dominate itself. And then we have that A is also in the post-dominance frontier because C post-dominates B, but does not post-dominate A, and A is a predecessor of B. Something cool. We can use the same algorithm to compute either dominance or post-dominance related facts. It suffices to invert the CFG. Perhaps you would like to check that this is true for these two CFGs? So once we have the notion of an iterated post-dominance frontier, we can use it to approximate the mid nodes of a backward analysis. In other words, if we have a dataflow fact appearing at a certain node n, then the mid nodes are the blocks in the iterated post-dominance frontier of n. As an example, where would you insert copies to split the live range of variable v used at block k? So here they are, the new instructions used to split live range. Notice that this time we are using sigma functions to split live range. Remember, we are talking about a backward analysis now. And once we have split live range, we can rename variables. We need to preserve the single information property. That is, the information associated with a variable is invariant along its entire live range. How can we do it? Would you like to think about it? Before I tell you an algorithm, or rather a principle to carry out this renaming of variables, just take a look into the transformed programs with every variable renamed. So, can you guess what's the principle that tells us how to rename variables? Basically, if the analysis is forward, we ensure that points where information appear dominate all the points where this information is used. And in the case of a backward analysis, we ensure that the point where information appears post-dominates all the points where this information is consumed by the analysis. One last important thing. After we split live ranges and run our analysis, we need to implement the copies used to perform live range splitting. How can we do it? If we use 5 functions, then we already know how to do it. That's just SSA elimination. But how can we implement, for instance, sigma functions? Well, a cheap trick to replace sigma functions with single array 5 functions. That can be done in the LVM compiler, for instance. And then we use SSA elimination to take care of these new 5 functions. So in this example, this sigma function has been replaced with 2 5 functions of single array. I mean, they take only 1 argument. That's okay. Thus far, we have seen 5 functions taking multiple arguments, but we can have 5 functions that receive only 1 argument. And we can implement parallel copies using ordinary copy instructions. There is even a paper about how to show that this implementation with single moves is correct. This is paper here from 2008. And with this last topic, we close this class on sparse analysis. Most of the developments here were taken from this paper, Parameterized Construction of Program Representations for Sparse Data Flow Analysis, published in 2014, so it's relatively recent. In the next two classes, we shall see examples of sparse analysis used in security and code optimizations that we can implement using the techniques that we have seen thus far.